Hello everyone. This is part 2 of the conversation with Eugene Goh, where we explore the global chip shortage, what the D1 chip means for Tesla, and its full self-driving ambitions. To better understand the conversation, I recommend giving part 1 of this podcast a quick run-through. This will help you better appreciate the scale of the problem and the solution presented. I hold this podcast as a hobby, and all my guests volunteer their time to come on the show. If you find the content helpful and would love to support the podcast, the best way is to like, share, and subscribe to the channel. Enjoy.
So now that we have a better idea of the entire process, we can really appreciate more how much effort just went into the Tesla DOJO chip, right?
Yeah.
So how significant, so what is DOJO for Tesla?
Right.
And how significant do you think it is for someone like Tesla to be working on something like this? Because you said, even for chip design, it's something that was in the making for at least a few years, right? 1-2 years.
Yep.
So someone inside has been saying, guys, we're doing this chip.
Yeah.
We're going to make our own chip. So what's your thoughts on it from someone who knows what the process is like?
I can make a few guesses.
Sure.
Basically, because you've seen hardware
Sure.
3. It's in your car now.
Yeah.
So that chip's been around for about, I think it must be about 5 years now, right? And hardware 2.5 was an NVIDIA device. So with hardware 3, that means Tesla had their chip design team for a while already.
Sure.
And because hardware 3 is their baseline now, it must be that they know that D1, which is the DOJO, and their whole DOJO architecture needs to work somehow, right? Because the information coming from there has to go into hardware 3.
Sure.
So I believe they thought all this out some time ago.
Sure.
Right?
Okay.
But they can target different technologies. So hardware 3, I think, is on 14 nanometers.
Okay.
But D1 is on 7. So they've already taken advantage of, they knew that they could take advantage of silicon integration and the technology improving. And that's what they've done with D1, right? But the system, the architecture of it, they have thought about it some time back. And it all kind of has to fit. But it may not be perfect because sometimes they may underestimate certain things. But it's a big effort, I'm sure. They must have thought through this, because if you think about the D1 chip, it's the building block that allows them to scale this huge supercomputer, which is DOJO. If they made a mistake in D1, they underestimated something, the impact is huge, right?
Sure.
So you need to think really carefully about what you put in that chip, how much memory you put in, what compute elements you are having in there. So that chip has, I think, a CPU, it has a GPU, and it has the what they call neural processor as well in it, right? And all that needs to use memory. So just to give you an example, Google made this thing called TPU, Tensor processor. And the first couple of versions, they suffered memory issues because they just didn't anticipate that that so much memory was needed. So they under budgeted on the memory, and that made them get stuck at certain things. Many have learned from it, so right, that Google themselves have learned from it. In fact, and so D1, one of the big things, and that's the one thing I'm most curious about D1. How did they come up with that number for that? I think it's 1 point something megabyte. I forget what's the amount.
I think there was a white paper that just got released recently. Does that?
Oh, that's for their floating point.
Okay.
But and that I think they thought about some time back. Right. But the D1, the memory and so the choices they make has huge implications later on, right? So that's the thing that it's always amazing for me, that how they decide. They must have done a lot of analysis. And it's a big team doing this, right? Trying to figure this out, and they would have done simulations to make sure that what they think they need, they put in. Because if they get it wrong, it's
it will set them back another.
It would. Or they would have to retool the software. There's a whole, or they have to, certain things that they're hoping to do, they have to hold it off, right? Or they have to push it. Some further down the road or something.
And the chip itself, like, during the event, I'm sure people who are not trained like myself, when we look at it, we can't appreciate the chip as much, right?
Okay.
So on your part, what was your first reaction when you saw the presentation, or like if you watched it, like what do you get from it?
So the first part about the presentation was the amount of bandwidth. That means the amount of data that they're going to push in and out of the chip is it's a lot. It's a lot. It's more than any other chip I've seen.
Can you give us a point of comparison, like just a sense of how powerful it is?
So normally chips, the I/O, so I was talking about I/O, which is the amount of data you can push in and out of the chip at any one time is defined by the chip itself, right? You have chip is, let's say, square. You have 4 sides.
Yeah.
They have, I don't know, terabytes on each side.
Okay.
Is it 4 terabytes or 2 terabytes? I forget. Yeah, 4 terabytes. That's a massive. I've never seen a chip with that amount of I/O.
So what would the normal like
half of that, maybe even less, right?
Okay.
And not on every side.
Sure.
Typically it's 1 or 2 sides, maybe 2 sides at most, right? That speed. They have that speed on all four sides. So that's...
And why do you think they did it that way?
I think it's the application that they want. So, okay, so the 2 things they want, right?
Yeah.
Lots and lots of bandwidth. Because, you see, with a chip, you can squeeze a lot of computation onto the chip as well.
Sure.
You can have the faster CPU and all that. But ultimately, your bottleneck would be how much data you can get to it.
Yeah.
So if you say, I want the most powerful compute elements, GPU, CPU, but I can't get the data in and out as quickly, I have a bottleneck. That's as much as I can process. So they approached it from, we want to make sure these computation elements never have to stall. Never have to wait for data. Right? So what I have to do is I need to start with what's the most amount of data I can get to this device.
Yeah.
And that must be what they were thinking.
Correct.
And then the other thing was latency, right? Latency is when you get data in, but you have so many steps inside the chip to process that data. The overall time is still long. And they're trying to reduce that because self-driving is real time, right? You cannot wait. You cannot wait for decisions have to be made then. So the real world doesn't wait. So you want your processing to be as fast, as little latency as possible. So it looks like those are the 2 main things that they were trying to achieve. Minimize the latency and maximize the bandwidth. Yeah.
Okay.
Right. And that was what's really impressive, because I have not seen chips that have done that in the past.
Okay. Yeah. Okay. And do you think that there's a chance they will put D1 into... So right now they're designing it for DOJO, right? Yeah. Is there a chance that there are other...
hard to say. It's okay. It's unlikely that D1 will end up in a car, for example. Yeah. That's unlikely because of the way it's designed. It's designed to be a part of a bigger thing, right? You can see they show,
make sure it can
they put 25 together and so it's all about that scaling up to make this huge supercomputer.
Okay.
And also, if you look at the other thing that was interesting was how they cool the thing, right? They had all these stacks of, and then they have the liquid cooling coming from the top. And because this chip is going to burn a lot of power, they have to find a way to, first of all, get the power into the chip. And then how do you cool it with the cooling structures on top? That makes it's specific to a particular physical implementation that they have to stick to. And DOJO is built on that, so it's built on this stack that they're gonna. The other thing about D1 is that it's not a chip that's going to be on a package on its own. It's what they call a silicon or die on silicon system on the silicon, where they have, even though the chips themselves are individual chips, but they are always going to be put in a 25 by 25 grid on this huge piece of silicon. Did you see that? Remember
yes, I saw it. Now I get it. Okay,
where the guy was saying, I'm holding 1 exabyte or something, right? That is always going to be...
He was so happy holding it.
Yeah, because that's an unbelievable amount of processing on just one piece of thing. It used to fill a room, right? That thing. And not that long ago either, right? but it's he holds it in his hand.
Yeah.
And they're gonna be stacking that.
Okay.
Right? Oh, it's not 1 exabyte. I think that whole thing is 1 exabyte. It's something ridiculous in that one piece, right?
Right.
And that's how D1 is gonna exist. D1 will always exist in that format.
Okay.
So it's not practical to. They're not even gonna individually package it.
Okay.
Right? It's always gonna be in that big slab.
Okay. So when you look at something like this, right? How profound is it?
It is very impressive.
Yeah.
It's not using any new technology.
Sure.
They didn't invent. I don't think they invented anything.
Sure.
It's all existing stuff.
Okay.
But just the way that they've done it.
Okay.
They're super ambitious. You can tell.
Okay.
They know exactly what they want. So, okay. The other thing about this is, they're obviously just going after this full self-driving, right?
Sure.
That means vision.
Yeah.
Processing, the learning and the AI aspect. And so they, in that sense, they could design something that meets this specific need. And therefore, they just optimize everything for that.
Okay.
Which is good, right? And I think that's what's impressive about it as well. Yeah.
So they're literally all in with the current suite of technology that they are deploying.
Right.
Like they're saying they're confident that this is going to work, and even if it's not, we're going to make it work.
Yeah, I mean they're committed, right? They're committed to vision only self-driving. And what AI Day, the thing that I took away from AI Day was the most was how they are all in on this.
Okay.
That means they are doing everything they can, doing some amazing stuff on the software side as well to achieve this goal.
Sure.
And the Tesla bot, interestingly enough, is actually one way of saying this is how all in we are, right? If we can, and we are confident that we can do this, and if we can do this, then what's stopping us from making a robot? Because what's one of the hardest thing about a robot is vision, right?
Yeah.
Vision is going to be the hardest, probably. Perception
and correct. Yeah.
And if our cars can be that clever in that space, then robots a no-brainer. Right?
Okay.
That's really what they're trying to say.
Sure.
The other thing I took away was actually from AI Day, right? It was another way of telling the world this is a difficult problem. It's a harder problem than many people think it is.
Okay.
One thing that Tesla does have is over-promising.
Sure.
Where Elon Musk does come out and say, oh, we're going to have FSD, we're going to have robo-taxis this date. I think one thing, I don't know whether you noticed that ever since AI Day, that stopped.
Okay.
They've stopped talking. Musk has stopped saying we're going to have robo-taxis. Then he stopped doing that. And I believe AI Day was the point where, I don't know whether it was himself realizing it or the engineers telling him or the other people in the company saying, I think we need to tell people we're not there.
Sure.
It's going to take time. But let's also show them how difficult it is. But also show them how far we've come.
Yeah.
So that they understand that we're committed to getting there. We will get there.
Yeah.
It's just a matter of time.
Sure.
But look at the tools and the development that we've done. And using that, we hope to convince you that we're going to get there.
Sure.
Of course, the other thing they said was to come and join us, right?
Yeah,
because we're doing all this great stuff. And if I was an AI engineer today, that's exactly where I would go. It's pretty amazing.
Sure.
What you're doing. Yeah.
Sure. Oh, that's a very interesting take back from yourself.
Yeah, because I was skeptical too, right?
Okay.
Thinking, really, they can reach level 5. They can have robo taxis that drive around on their own with passengers. You don't know. Is that something they know that we don't, right?
Sure.
So with AI Day, then you say, okay, they're trying to tell us it's not so easy.
Sure.
But they're working on it, and they have what it takes.
Sure. And it's so now that you mentioned this, right, it's very interesting to know that in order to solve FSD, right, to solve the idea of level 5 autonomy, so much work has to go into it, and right down to designing your own chips to put it into the neural net so that it can really learn from so much data that are going in and push this out to the different vehicles out there again. So how far do you think Tesla is from FSD? 5, 8 years?
It's hard to say.
With this new processing power.
Yes. So what we show in for sure DOJO is going to help them get there much more quickly. But I think DOJO maybe is still about 2 years away.
2 years away.
I'm not really sure how much computing power they have currently. I think they're using NVIDIA as a sort of supercomputer, right?
Sure.
And that's actually doing the training the data that goes into your car now, right? It's coming from that computer. I'm just thinking, so, okay, with AI Day, they showed things like that vector space. I don't know, right? So
it's amazing.
That was impressive.
It's so impressive.
That's impressive because
that was so impressive. Okay.
That's really taking. You know how video and pictures are 2D, right?
Correct.
It's all rasters, nothing. It actually doesn't say anything. It's only what your eyes see.
Correct.
So how do you tell the computer, right? They're training your AI. That's what it is. So they have all this thing about translating it to 3D in a vector space because that's easier to manipulate and label and all that sort of thing. So I think it's with that. I mean, if they weren't doing that, with rastering, you'll never get there. So with that, I think they're maybe 3 years.
Okay.
Right. The other thing that was impressive was the simulation. Did you see that?
Yes, I saw that. So it's, oh my god, so
that's
good.
for corner cases.
Yeah, it's
right.
Yeah.
But it's interesting that it's because they went into the vector space. Therefore, the simulations can help them because then it becomes part of the same data set.
Yeah.
Right. The training computer works on the vector space. Your simulations are essentially vectors. So then they can feed that 3D information with all the mistakes that the simulation, because it is what's helping the computer get smarter, right?
Correct.
All the collisions or whatever, or close calls, right? That's what they're trying to simulate and reinforce the training.
Sure.
The thing that I don't understand actually at this point is how once they've trained up this really smart self-driving capability, how it gets translated into what hardware 3 can understand and then use. That part I'm not sure.
Okay.
It's something to do with they have to then pick the things that matter somehow. You know how in AI it's this big neural net, it's just again millions of these knobs, right? Billions of knobs. It's which knobs matter and then translate that into some kind of memory map that gets downloaded into hardware 3.
So what's the difficulty with, let's say, whatever that you have on neural net and then you bring it down to your car? Like you said that there are some portions where you don't understand so
because it's a lot of information, right?
Sure.
Okay, maybe there are certain things that are not. So with the training, you need a lot more information.
Sure.
Because how accurate your neural net is, or how accurate or how good your predictions are, and your decision-making processes. So like humans, we make decisions. We make the best decisions based on good data.
Sure.
So good data means training, right? So it's the same with the AI, right? The more good data you can give it, the better it's able to make decisions and make predictions. But how you can't possibly store all that data in hardware 3. So all that data is in that neural net. The decisions that it makes, or there's the map of what decisions it can make and how fine it can make that. So there's a fidelity thing as well, because there's a trade-off. You can go very fine, that means you can look at all the little details, but it may not help you. Maybe you only need 25% of the details to make the decision, even though the neural net has all of it.
Sure.
So then the thing is, how do you pick how much of the detail you need that is sufficient for hardware 3 to make the decisions that the car needs
to make? Okay, I get it now.
Right?
Yes, I get it now.
I think that's kind of what it has to happen, but as to how they do that, I'm not sure.
Okay. It will be interesting to see how much data is being stored in our car, right? So what is the hardware capacity of our hard drive, for example? Like how much data is being kept inside?
That one is a mystery. I think that must be a pretty hard problem, right?
Yeah,
in fact, my fear is that when it's all kind of said and done, in other words, when their neural net has reached a point where they say, I think we're there. What they eventually pick
and send over to the car
it's too much for hardware 3. hardware 3 is not able to cope, and they say, you know what, guys, actually we need hardware 4, right, or above, right?
Sure.
I think that could happen.
Correct.
That could happen.
And the thing is, we constantly underestimate the future.
Exactly.
Yeah. So even you can plan like for so many redundancies, and when you finally reach that, you're like,
yeah,
even that was not enough.
I underestimated the problem.
Yeah.
And that's happened before. We know that, right?
Sure.
So we'll have to wait and see.
Okay. How much more powerful is DOJO compared to, let's say, NVIDIA back then? Like just off your head, like maybe from what you saw.
I'm not sure about the sort of actual computing power, but from the looks of it, it's much more optimized for what they want to do. I think that's the main thing.
Okay.
The main thing is, so okay, they did say, I think it's 4 times.
Sure.
Now, at that scale, that's massive, right? 4 times. Yeah. And I think they realize now that if they don't get that kind of improvement, they can't get to where they want to go.
Okay.
Right? So, well, they must know already that this is what they need.
Sure.
It is, as a training, as a piece of compute.
Sure.
Platform for training vision. I don't think there's anything in anywhere else that matches it.
Sure.
Yeah.
Okay. So, I had something off my head. Now I got a roadblock on it. So I can't think of the. Yeah, I kind of lost it with DOJO, but I had something in mind I wanted to ask. Yes, with Tesla, do you think there's an opportunity for Tesla to ever be a fab?
Oh,
because if
I think that's unlikely.
That's unlikely, right?
Because fabs are so expensive.
Correct.
It's probably, you know how Tesla they're really in the space where they are experts, right? They are the domain experts and leaders in that space. A fab would be, they wouldn't.
Correct.
You know, it took TSMC 30 years or 40 years to get where they are. Intel even longer.
Yeah.
I don't think it's a business they want to be in.
Sure.
And I don't think they need to be in that business.
Yeah.
Right? If you look at what Apple is, even Nvidia, right? Some of these fabless has proven to be a good a good business model.
Sure.
Now, what I think they may do is to have closer partnerships. So you think about how Apple is able to secure their silicon, and even then they're struggling now, right? But they have very, very good relationship with TSMC. And somehow they can guarantee the capacity because they drive such big volumes, right? So I think for Tesla, they may try to get better partnerships with these fabs so that they can secure the capacity better and not run into the problems that we're facing now with shortages and all that. I can see that happening.
Sure.
It may have already happened.
Correct.
But as a fab, I don't think so.
Sure. Yeah. So even TSMC themselves, they do say that we will never compete, right? We will never compete. Right. So that's very interesting. So I think a lot of people are saying that one day Tesla can be a fab themselves, but the amount of investment you require. Like manufacturing is painful. Like for people who know the process, manufacturing is not easy.
And I don't think even when they start making 20 million cars, right, which they are predicting, they would ever drive the kind of volume that, let's say, Apple drives, right?
Correct.
Apple drives maybe 3-4x that.
Correct.
So even then, they don't need a fab.
Yeah.
So I think it's unlikely.
Yeah. It's interesting though. I'm curious what SpaceX is using.
Oh, so
sorry, this is our topic, right?
Yeah, SpaceX. They have to use all the aerospace.
Will they be using something like, they won't need any vision, right?
SpaceX.
Yeah.
No, that's different.
Sure.
I think the AI I think what SpaceX can benefit from is the robots.
Sure.
Right, Tesla bot.
Correct.
Instead of high risk stuff that they do in space, let the robots handle it instead of humans. But SpaceX, I think they're like, I mean, there's some sharing, right? You know that heat pump in that Model Y that came partly from SpaceX. But I think for electronics, not a lot because it's so different.
Sure.
They need all the fault tolerant stuff. In fact, when you go to space, the chips you use are a lot less sophisticated. They're a lot more hardy.
Okay.
But the amount of processing power you can pack into it is much less because you need all this redundancy, right? So maybe it's about, at the best, a third the power of a chip that is you use just daily.
Okay.
And they need more.
Okay.
Right?
Yeah.
And that makes it expensive and complicated.
Sure. Were you trying to say something just now before it's about SpaceX?
Yeah.
Sorry.
So my company does we do supply SpaceX stuff, and in fact, I don't know whether, I believe some of the, what is that? It's all those satellites going around.
Starlink.
Yeah, they use FPGAs.
Okay.
For that Starlink stuff. Yeah. I don't know which type, but I think they use some of those chips.
Okay. That's interesting. That's nice. So what's with the chip shortages that have been going around? Like why everyone is saying that there's a chip shortage, even from Apple to Tesla to your auto manufacturers. Like what's okay? So maybe first we start with the auto manufacturers. Like why are they having that issue?
And why Tesla doesn't, right?
And why Tesla?
Really.
Like affecting them a bit less, right?
A bit less.
And then we'll go to something more macro. So let's start with the auto manufacturers.
Okay. Yeah. So for the auto manufacturers, I believe the problems come for a few reasons.
Sure.
Firstly was when last year this big shock to the market, right? Yeah. This big scare, everything was dropping.
Sure.
So a lot of auto manufacturers cut their production. Now, and when they cut production or they forecast a much lower, they thought they're going to sell less cars. But what they immediately do is to let their supply chain partners know that, we're going to buy less stuff.
Sure.
Okay, so then it became this kind of perfect storm thing where you tell your suppliers, including your chip suppliers, that I'm not going to order so much stuff. So the chip suppliers would then divert the capacity that they reserve for you to something else. Now, it'd be okay if that something else says, we also don't need.
Okay.
But actually what happened was that something else say, we need more. Because people started buying more PCs, laptops, and all sorts of other things, right? So some of this capacity would go to these other things and then may not come back to the auto guys, or rather the fabs will say, okay, so you forecasted, maybe you take half of the number of chips you normally do.
Yeah.
So I've given all that to somebody else.
Sure.
And they say they want it for even longer. They want even more.
Correct.
Or they want it for even longer. So I can't really give you now.
Yeah.
If you want it, you just have to wait.
Yeah.
Right?
Correct.
So then they're stuck. So there are two things they can do. They can go somewhere else.
Sure.
But it means not so straightforward, right? They can't redesign the chip. There's a whole lot of things that need to happen. So that's why they're stuck in this.
Okay.
Right? And I'm not sure how long this will last because that happened last year.
Yeah,
it may be coming back now.
Okay.
Then there's another problem. Okay, so some of these fabs, typically they make, the chip cycle has this kind of like a curve where when I'm making a new chip, like new technology, 7 nanometer, all that, as there's something called yield. That means how much I can get out of the factory that is good versus bad, right? The higher the yield means I get more good chips, right? The yield has a curve that increases as the technology gets more mature.
Sure.
As yield go up, your profitability also goes up, right? And then but it reaches a plateau.
Yeah.
This is how much money I can make.
Sure.
Then what you hope is that your next technology comes in with another curve
that is higher than
because as the technology gets more mature, the people buying the chips will start to come asking for discounts and know. So then your profitability will start to
reduce.
Now a lot of these auto manufacturers are using very old technology.
Okay.
Where the people who supply the chips don't make as much money, right? Now if I have X fab capacity, I would want to maximize this capacity for things that I can make more money. Right?
Correct.
So why would I want to continue making these older chips where I'm making not as much money, and I'd rather supply to people that give me better margins, right?
Yeah.
Then I would tell the auto manufacturer, sorry, my capacity is going to do things that are making me more money. Do you want to pay more?
Yeah.
Right?
Or do you want to change your chip design?
Yes, exactly. Okay. So that's the other problem that they're facing.
Okay.
And that's happening not just to the auto guys, but throughout the industry.
Okay.
Yeah, that's it's just how it works.
Yeah.
I mean, if it sounds like not fair, right? I mean, it's a business.
It's business, right?
So unfortunately, that's how it works, right?
Like fabs are not cheap.
They're not cheap. They have limited
capacity.
And now the demand is more than capacity.
Yeah.
But if I was TSMC and I'm saying I'm building new fabs in Arizona, in Japan, I need money, right? Capital. So I must maximize my profits.
Sure.
I must make more money. If you want me to invest in more capacity, I need to pump in. You're talking about tens of billions of dollars. So I'm going to optimize my business to make me more, right? Then those things that are not making me money, maybe I don't want to do so much.
Correct.
That's just the way it is, I guess.
Okay. So this has spilled over from. So why is it that so the old guys who couldn't do it, number one is the chip design is old, right? So it's a very mature technology that perhaps the fabs nowadays they would prefer to do something that is more profitable. So how do you think Tesla managed to navigate this situation? Like, was it simply just a supply?
It could be. I think Tesla, because Tesla has always been they're constrained by how many cars they can make, right? They've never been in this business that they have to slow down how fast they make cars, because the demand is way more. So they wouldn't be one of those people who during the downturn say stop, don't make so many chips for me. They would say just keep going because
you need the stuff.
I need the stuff. So they probably didn't get affected by that. But I think they may have. So maybe hardware 3, which they keep needing those, they didn't stop that. The place that maybe got affected was possibly other electronics that are more common. It means shared with other. And for that, because they're so they're software driven, right? Their car is mostly controlled by software. They basically just redesigned their software to use other chips. And in fact, Musk came out to say that. It took them, I think, 3 or 4 weeks to rewrite the software so that they can use a different chip. Or chips that are in bigger supply, better supply. That's the beauty of Tesla, I suppose.
And arguably, it would have indirectly may have helped them also, because then it made them relook at a process that probably was about right now maybe about 6 to 8 years old already, and then they can say that, okay, look, since these old chips were gone, like how can we redesign it or even look at it and change it such that it's more efficient, and something like this does not affect us in future. They can look at
exactly.
They can even have the opportunity to
And I think they are ahead of the game because they kind of were thinking that all along, and because they're it must be because they always think of software first. And then this kind of justifies their position as maybe for this sort of thing, if you use more software, you're less dependent on componentry and it's interesting. If do you follow the markets?
The which
the financial
markets is it like just stocks and
stocks, right? Apple had $8 billion of short on revenue. What was the other company? Well, maybe Apple and maybe some of the other system builders, but Microsoft is all time. So if you're a software person, you're not affected by this, right? And that's so clear. Apple, a company that always hit its targets in the past, even they are struggling, right? They are they must have the best supply chain partnerships of any company.
That's Tim Cook's specialty, right?
And even that affected them. But Microsoft is gangbusters, right? It's like it's 20% increase in revenue. So that shows how clearly the component shortages are affecting people. Even the big boys like Apple.
So why do you think even people like Apple is being affected? Is it just more demand, or is it has supply? Supply.
I think supply, because so it's not just about the chips. It's everything else, right? So there's memory, capacitors, all the discrete components. So if you look at any average motherboard or it's a lot of stuff. And all you need is for one thing to not
be there.
You can't ship it, right? Your thing is not complete. So it could be any one of those things, right? That Apple just wasn't able to get as many as they wanted. Usually it's not the chip, because that's theirs, and they will probably forecast they're gonna, and especially when they share For example, the A15 chip, right, also goes into the iPad
iPads,
and all that, and the M1 chip goes all over the place as well.
Correct.
So those, I don't think supply shortages affect them. It's more other things like memory, where they're also competing with
other manufacturers
for the same memory. Capacitors, those kind of discrete components.
Yeah.
And now, especially for wireless devices, there needs to be special capacitors because of the circuit requires certain things because they're running at such high frequencies. So our phones are at 20 gigahertz and everything. So at those frequencies, you need special components.
Okay.
And those are always in short supply. Or rather, you're fighting with Samsung and anyone who's making a wireless device need that, right? I think there's also not enough. Right. Then one is because there's so much, the demand has just raised ahead of supply.
And no one saw this coming,
and the manufacturers did not foresee this huge surge in demand. The other thing about chips that's interesting, and in fact it affects many companies, is that the chip itself has not just a silicon wafer, right? There's something called a substrate that the wafer sits on before it goes into the package. Again, if you could have lots of wafers, but if your substrate is in short supply, you're also stuck. You can't ship your chip. And that happened quite a lot. Because the substrate manufacturers are not as well, they don't invest as much in future capacity as wafer fabs. So there's this imbalance where you can have a lot of something and not enough of something else. The end product is only as good as anything in between, right? The supply of anything in between. And that's some problem that we're seeing too.
It's interesting. The supply chain is a very interesting thing. Because it's so capital intensive, right? Even if TSMC wants to do more, or even if they would try to vertically integrate more, it's so difficult because just to do what you currently do, you have to achieve scale. And if you don't get that scale, you can't doing something else that is on the horizontal, even though it may be just one step down for you, like upstream or downstream, you need that scale. And if you don't have that scale, you're
kind of stuck. And it takes time and it's expensive. So TSMC's fab, how quickly they can build a fab, it's not just the concrete it's how quickly can ASML provide them
with the
machinery.
Machines also, right?
And that machinery is also, Intel wants to buy it. For example, in that particular part of the process, I think the EUV one, right? ASML is the only company that does it. So can you imagine they're supplying to Samsung, Global Foundry, so many companies. If you cannot get your hands on that machine, you got no fab. You can't do anything. You just sort of wait for it.
And they're only producing about 20 plus a year, or
and it's like, I don't know, tens of millions of dollars a machine, right?
And it's so sensitive to ship, right? Like if you knock it or you damage it a bit, and those instruments are so fine, like you said, right? You're designing on a
And so the calibration, the maintenance, it's a huge effort. The more you think about it, you think, wow, okay.
It's massive, right? This whole thing is massive. It's not easy to get physical stuff done. No, Microsoft. Thank God they ran away.
Right. So now you're seeing where the money will flow to in the shorter term.
But it's important to invest in hardware, right? Like, so even for someone like Microsoft, right, someone may be able to meta you. If like, of course, I mean, if you're integrated to B2B, then people don't move that fast, right? But hardware, once you're there, who's gonna touch you? Like TSMC. For someone to touch TSMC, like China is trying so hard to do it. Right.
It will. I mean, with enough capital,
with enough money, you can.
You can, but you see, it's also partnerships, right? Like ASML only makes so many machines a year. Who are they going to sell to, right? If there's 40 people, they make 20 machines a year, but they need to supply 40, they will decide who are the first 20 that get it. So even if you say, I've got tons of money, I want to make a fab to catch up with TSMC, do I have access to right?
Right.
Okay, the other thing you can do is you can make your own ASML, but there is a reason there's only one in the world.
Correct.
It's not easy, right? So
and it got blocked.
Yeah. So you think about how quickly can you try to adapt to this?
Yeah.
It's not easy. It'll take years.
Yeah.
Years and billions of dollars.
And the right talent.
And the right talent.
And you don't have that many people in the field also.
So even though you have to respect China for trying to become independent and not dependent on.
I can imagine.
But
it'll be
but it'll be a challenge. I mean, it'll take time.
I believe they can do it.
Yeah.
And it's the right thing. They have to do it.
Yep.
Like they have to, right? There's no chance that you're gonna let other people. You're so big.
And they should.
They should
too, because you want competition is healthy. You don't want one guy to control everything.
Correct.
But yeah, it's not easy.
It's not easy. Yeah.
They're gonna have. I don't know. I can't even see. This kind of ASML stuff is a big thing.
Yeah.
Where are you gonna find another guy who's making this stuff for you?
Correct.
Right. Maybe the way to do it is to go in a different direction. Research a new material.
Correct.
And maybe make chips with different machinery, different process, and that's maybe the way to do it.
Like really rethink relook at the problem and then see whether.
Perhaps that's one way to do it. But whatever it is, it will take time and money. Yeah.
Yeah, it will really take time. So okay. Anyway, so if someone who wants to get into this field, maybe also on your part, right? You can share like what's interesting about it, and if I were to want to join the field, like where do I start?
So if you start in school, typically we do math, physics would be maybe chemistry as well.
Sure.
And then as you go to university, electrical engineering, even computer engineering, both would be suitable for if you want to be a designer, chip designer. And then what you can be assured of is, as a designer, you will use a lot of what you did in university. In other words, the things you learn. You know how a lot of times I've heard people say, I started work, I used almost zero but for an IC designer, you will use a lot more.
Okay.
Right? Which is, for some people, that's good because they enjoyed what they learned in university and engineering courses that they took. Then you would continue to use the skills that you've picked up in university.
Sure.
And then, of course, for people who like to understand a little bit more what goes on in these in chips, in systems, in our gadgets, that's one way to go and learn more.
Okay.
It's quite rewarding because it's nice to know that you worked on something and then you see, hey, look, it's in this car or it's in this phone.
Correct. And for you, like maybe it's in space, right?
Some could be in space. A lot of the chips that I've worked on are in, when we make a call, the phone talks to a base station, right?
Okay.
A lot of chips go in there.
Nice.
So you think, well, every time someone sends a message, makes a call, it's you. That data is passing through some chip that I've worked on.
Yeah.
It's pretty fun to think about it, right? But the nice thing, of course, it's so fast moving, so you just have to keep learning all the time.
Yeah.
So it never gets boring.
Okay.
And that's, I think, one of the things that I find most fun about it.
And you've been in the industry for?
Since I started work. I've always been in this job. I mean, I started as an IC designer.
Yeah.
I don't do so much design these days. I don't actually do any.
Okay.
But I'm still involved in it, obviously.
Okay.
Actually, one interesting thing about my own career is I've never written a resignation letter, even though I've worked for 4 different companies, coming to 5 now, right?
Okay.
So I've always been, I started in AT&T in Singapore, right?
Okay.
And then it got spun out. The department I was in got spun out as Lucent Technologies.
Okay.
Then that got spun out as a Gear Systems.
Okay.
And then a Gear Systems, I got retrenched from a Gear Systems.
No shit, okay.
The Gear Systems eventually got bought by LSI.
Okay.
And then now got bought by what was then Avago and then Broadcom now. And then when I got retrenched, that entire team that got retrenched then got acquired by Xilinx, which is the company I work for now.
Sure.
And then Xilinx would probably become AMD. So I would have worked for 5 companies, never having resigned from any one. Yeah, I've never. I basically I don't know how to write a resignation.
Okay, that's interesting. And is there a chance for someone who is mid-career to have a shot at even joining you guys? Like, let's say if I'm not trained, right? Like, let's say I came from a science background, maybe physicist or a mathematician or even an engineer, right? Is there a chance to join you guys?
There is a chance. I wouldn't say no. It's going to be difficult.
Sure.
Because the steep learning curve is pretty steep.
Sure.
But it only if it's difficult, right? Because it only if you're willing to start from scratch.
Sure.
Right. So it's a very competitive environment. It is, right? You got typically in an average design team, you got pretty smart people, obviously.
Sure, I can imagine.
And they are competitive, and they are naturally competitive. They are all very analytical, and so they've spent time learning and getting where they are. For someone who coming in to start from scratch, you must be willing to start from scratch in terms of your salary as well. You're willing to take that cut in pay. I think most companies would give you some buffer in terms of, if you worked, let's say you've worked 5 years in another industry, they'll maybe give you 2 years recognition that, so your pay won't be rock bottom, new college grad pay. But you will probably have to start even at a level, a lower level in terms of your pay grade kind of thing, right? Yeah. That's the thing that I think would discourage many people,
right?
Unless it's something that they're really, really passionate about wanting to get into. Yeah, they may be willing to take that, but I've not seen that ever.
Really?
Yeah, I've not seen anyone do that.
Okay.
I've seen people say maybe they worked a couple of years as a test engineer or product engineer and they didn't really like it, and they feel that design is something they want to try, so they made that switch.
Okay.
Maybe up to about 3 years in another industry, probably the salary differences won't be so much, and it's probably acceptable for still most people.
Sure. I think it's one of those things where university is the filter for you, right? Like if you're gonna go into the field, high chance you have been exposed to it somewhere during education stage. It's one of those things where it's not, I won't say it's not sexy, but it's not in the face, right? It's not very face value kind of a product. Like people, you have to be interested to know that, hey, what's underneath my iPhone? It's okay. You get what I mean? Like it's something where you really have to be curious about,
right?
And then it will get you into the industry.
So, what happened? There was a period where the chip industry got a bit commoditized, unfortunately.
Okay.
In other words, people started. There were more generic chips like CPUs and all that, right? And they could use it for different things. Then people started to feel that chips are just another commodity, right? I just buy memory and I can put things together. There was a time, maybe in the late 2000s, early 2000s, late 90s. But then now it's gone the other direction, right? So you see all these big companies like Amazon, Microsoft, now and Tesla, of course.
Sure.
They all have their own chip. Like Google, another one, right?
Revenge of the chips.
In fact, I think Apple has a huge chip design team. And then the chip now is the differentiator. It's the thing that says, look, this is why my MacBook can operate for 20 hours. When the Intel laptops run out of battery in 10, right? It's actually a lot to do with the chip, right?
It is.
And then people say, okay, that's the differentiator now. And similarly with the phones, right? And that's happening throughout the whole stack. So, at Tesla says, no, if I want to do vision AI, the NVIDIA stuff ain't gonna do it. I gotta make my own, right? And then people start to realize that it's a key part of the technology advantage now.
So it's kind of like a cycle, right? You reach a point where your hardware has hit this is as much as it can do,
Right.
and then software has to catch up.
Right.
But then once software catches up, and then suddenly your hardware is behind again. So now the resurgence for hardware is back.
That's right.
Like with vengeance, right?
Because it's become the differentiator.
Correct.
It used to be, I just made my software smarter, I could differentiate.
Correct.
Right? But now it's starting to see, okay, this software is going to reach its limits because the chip is slowing everything down.
Correct.
So I need to make a faster chip, and then I might as well make one that has all these advantages that I want. So I think, I'm hoping that because of that, it would bring more people into the industry.
Okay.
Yeah, that people will be more excited to join the industry and no longer feel that it's, the domain is now software. It's software's world now.
Yeah.
I don't think that's true.
Okay.
In all aspects, right? And hopefully more smart people will continue to join the industry.
Sure. Yeah. I think it's interesting. There was a time where people actually laughed at Apple for using their own chips in their Macs, right?
Yeah.
And it flopped so bad.
The PowerPC time.
PowerPC time.
So they went to Intel.
Correct.
And now they're back. Yeah. And now people are copying them, right? Intel is kind of, although I'm sure Intel had that architecture, the Alder Lake one, some time ago, but this heterogeneous way of doing cores looks like it's the way to go.
Yeah. I think we'll see that trend in the next. It'll be interesting the next few years, like how much more we can push.
Yeah. And I'm excited by this optical one, right? How far they can push that, using light into the device. And then because that's going to drive huge amounts of bandwidth.
Yeah. Let's see how the D1 once maybe the next year when they have the next AI day and they share how profound the effect is.
I mean, then you see maybe when DOJO gets turned on and starts doing its training, you see huge improvements in
almost like Skynet, right? And DOJO gets turned on. It's like, oh shit, Skynet is here.
It's gonna be pretty exciting. I think
and even Google has their own Tensor chips in the phones right now. I think the Pixel 6, there's issues, but I'm sure eventually that's a trend. Already.
It's a trend. In fact, even the normal Apple, the A15, the A15, they have their little neural thing.
Yeah.
And that's to do that facial thing, right?
Yeah.
Voice recognition. So the general neural processing is good for that.
Okay.
Whereas I think Tesla's is just vision mostly.
Sure.
Yeah.
Sure.
The voice stuff is, I think that's they're pretty much solved that, right?
Yeah.
These days, voice recognition is so good.
Yeah. Interesting. All right, Ken. So I think what we'll do is we'll try to put some links. So in the comment section, maybe we can both compile some good starting points if someone who is interested in the industry.
Sure, I can provide.
I think that would be fantastic. And then also perhaps the courses that people can look at or
I think I have access to some of that.
I think resources will be interesting, right? So it's more of like how do we get like we can't change, like you said, right? Switching mid-career might be a challenge. Like if you're willing to take up a challenge, please you can go ahead and try it. However, if you're young and you've got the energy,
go for it. I would say
go for it, right?
Go for it.
So let's just put it out there so that whoever that we may touch can have a good shot at this if they want to.
Right.
Yeah.
I hope so. I hope some people will come and join the industry.
Okay. Ken. I think
thanks for that.
With that, I think we're good. I think we'll probably have to do a 2 parts for today, right?
It's run quite long.
It's run quite long, so we'll probably do like an introduction to chips, and then we have a segment for DOJO.
For the DOJO stuff.
And then but more or less this.
Because we started at maybe about 9. So it's about 1.5 hours. Wow, that's a long video.
And it's heavy, right? The topic is not something where everyone can.
It's quite heavy.
Like even for myself, like I only started really getting to it 20 minutes in, like when you start giving me more context. Really explaining to me. And this is not accounting for the fact that yesterday I spent a good 5 hours, really trying to read up things. So I wouldn't have known about the whole steps that was involved. Prior, the architecture, the chip design, the fab. It's very important to see the big picture, right? So you have one industry, where are the different components of it, where you are, and how it affects the entire thing. That is important. That one shot can give you a much better understanding.
And it's not easy for me to think as well in terms of trying to put that. I was jumping about in some places, right? But
I get it, because you're very into one vertical of it, right? And there's so many within that one vertical. There's so many of it, but yeah, when you are in that vertical, you see how complex it is. But then, like let's say from someone for myself, like I'm on the outside, right? Like it's just so much.
There's so much going on inside. In fact, there's a team.
This is the end of part 2 of this podcast. Eugene and myself hope to inspire you to pick up and learn something new. If you're still starting out, he has very kindly compiled a list of links that will give you more information. Thank you and have a great one. Hello everyone.
Sorry. I missed the table. Sorry. No more.